About 10 years ago I worked at Trolltech, a small Norwegian company making tools for developers to build beautiful applications. I worked there for some years when we got acquired by Nokia. Nokia wanted our development libraries to work fast and smooth on their phones as well as on traditional desktops. As this was a developer-driven company, many developers came up with solutions on how to reach that goal. These developers showing off their ideas meant we had lots of awesome projects to choose from. These projects can roughly be split into two sides. The optimization side, which easily fixes 100 little speed problems, and the big changes side. These are projects that require much more time because they change the fundamental ideas, but they do have a lot larger return on investment. So I would think that Bitcoin is in roughly the same position now. We have to get better and we have to scale Bitcoin for many more expected users coming in over the next years. Now, thinking back, my experience with this process in Trolltech was that all the small, low-risk changes to make it faster were a huge success. They were needed and they made a huge difference. On the other hand, the larger, big changes inevitably introduce more risk, and they force people using our software to change their behavior to actually use the new concepts and ideas. So after they change their behavior, after they use some new concepts, new techniques, new tools, only then would they gain the benefits of our use, of our work. For these reasons, the effort to do the big changes ended up taking several years to actually bear fruit. In the end, both groups pulled it off, and the results are, in my personal opinion, simply unique and amazing. Some lessons I learned from these projects at Trolltech are: we do need researchers to do what they do best, come up with strange and exciting ways to do things better, make radical changes, propose them. If they work, do it. If not, then we can try something else. But we also really need people doing the boring optimization work. Making protocols, networking protocols, work faster and more reliable. As a simple example. This on-chain conference presents various optimization level changes that will make Bitcoin scale much better than it does now, with very little pain, and from experience I expect quite a big gain. We call this on-chain scaling because whatever your belief is on which path leads to Bitcoin success, if we want to scale, we need on-chain transactions to scale beyond the current 3 transactions per second. For the next year, some changes are being prepared, which, by the nature of them being fundamental changes, the big changes, the fundamental changes in the way that Bitcoin is being used will take much longer to create and roll out. I've seen plans like Segregated and Witness and Lightning Network. They're very interesting ideas for sure. Various teams are working on that, and I will wish them all the luck. To me, it is already clear that we can't expect those scaling solutions to have any reasonable impact without on-chain scaling solutions being rolled out as well. And this makes sense, of course. When you think about it, you need the foundation to be strong when building on top of it. Now, enough with the high-level talks, let's see some actual ideas. This here is the idea of Bitcoin. We have a single computer that receives transactions and groups them all in its memory pool. What it does at the same time is Bitcoin checks each of those transactions for validity, and after some time those transactions are combined into a block. This is very basic, but please bear with me. I'm just going over the basics for the people that haven't really caught up just yet. Every single transaction entering this Bitcoin computer is checked that the transaction is a legal one. For example, a payment from person A to person B can only be created by person A. We use cryptographic proof to check that a person initiating a transaction is actually the owner of the coins he or she is sending. Bitcoin also checks that people don't try and send digital coins to two people at the same time. The Bitcoin application holds all transactions in storage, and if one comes in that tries to spend an already spent money, then it's killed. That's a cheater. Go away. When a block comes in, it makes the transactions contained in that block permanent, and Bitcoin will merge that block into its database. The transactions it had in memory are now removed if they were already in this new block, or no longer valid because of other transactions in that block. The thing is, Bitcoin is essentially operational with just one node, but it works with duplication of its functionality over different nodes. Here on screen I present 5 nodes. When a transaction comes in, the node validates it, and if it is valid, the node will forward it to all of its neighbors. These do the same thing and forward it to their neighbors. The measurement we've done is basically saying that in less than 1 second, 50% of the network will have the transaction. In less than 4 seconds, practically all of them will have it. These nodes are in many respects exact duplicates. So technically there's little reason to have more than one node, except maybe failover. Politically, this duplication does mean we avoid centralized decision making. We avoid only one operator being able to tell us what the rest of the world being able to tell the rest of the world what Bitcoin will look like today. This is assuming we make the system work fast enough. Blocks, the big collection of transactions, get copied between nodes as well. The propagation path is similar to transactions. Currently we send blocks as a complete chunk of data in one go. This is then validated by a node to follow the Bitcoin rules and forward it to its neighbors. A healthy network has a large number of Bitcoin nodes to ensure operation and to allow some of them to be removed without harming Bitcoin as a whole. Damage to any part of the network will just get routed around. Naturally, with a large number of nodes, how they are networked together becomes more important, and that networking layer itself becomes a source of failure. So the part I've skipped over so far is where blocks actually come from. The answer to that is a block is created by a miner. See, here's one on the left bottom corner. The miner created the block and sends it over the network. Each node turning blue means they received the data. Now, a block is actually a substantial amount of data, and it will take longer than 1 second that a single transaction took to propagate. BitcoinStats.com reports between 10 seconds and a minute to propagate a 1 megabyte block to practically the whole network. So if we start mining bigger blocks, this time will most likely go up, because obviously more data means slower propagation time. As the mining difficulty is adjusted every 2 weeks to make sure that the time between blocks stays on average 10 minutes, we can assume that as a standard, a stable number. And that basically means that the time it takes to send an entire block is not really a big deal for end users, as long as they can download blocks faster than they get created, in this case once every 10 minutes. Things will continue working just fine for them. Not optimally, but it works. There are many people using Bitcoins that on the other hand have higher requirements though. And the current way that Bitcoin works leaves a lot of space for improvement. I am currently focusing on miners. How to make sure that miners get the best out of the system, basically. To explain what I'm working on, I will first show you what happens with miners using the Bitcoin software. I'm going to draw a line to separate two miners, top and bottom. I'm going to draw the time as shown from the perspective of two miners, one at the bottom, one at a physical different location at the other side of the screen. Now, two miners are mining, and one finds a noun that makes his block valid. So this miner is really happy. He just made several thousands of dollars worth of money in Bitcoin. At least as long as he can convince the rest of the world to use his block. He just completed building, and the rest of the world can build on top of it. This does imply that his block is seen and accepted by the rest of the network before any competing blocks are being sent to them. To do this, he sends this block over the network to another miner. The mean propagation time measured by Peter Ruzin, this is for blocks between 900 kilobytes and 1 megabytes. The mean time shows about 4 seconds. But as soon as you hop over the Great Firewall of China, that rises to a mean of 17.4 seconds. So this is really a relevant number. I use the real-time example here of 10 seconds because mostly I don't talk so fast anyway. Now, after the miner on the bottom received the block, he will be able to start mining on top of that. What you may notice is that the miner on the bottom is essentially doing work for about 10 seconds. That is useless. He's still competing on the competition for block 1, while that race has already been won by another. He just didn't know that yet. So I'm going to talk a little bit about something I called optimistic mining. A proposal I made, which is still in development, it tries to fix this specific little issue. So, same situation. One miner finds a block. Hoo-hoo. Here's the difference. I split up a block into two parts. One is teeny tiny and sent over the network and close to the speed of light, and the other is the actual block, unchanged from before. While the entire block is being sent, the miner at the bottom is now all of a sudden able to mine on top of this new block because he received the little tiny part of the block already. Therefore, he's no longer losing money doing work that is useless. Because the full block with all the transactions hasn't arrived yet, this miner can't actually know which transactions are included in that one. And that also means that he can't figure out which transactions are safe to include in his new block. The solution for that is simple. His block is going to be empty. The miner will switch to mining a full block as soon as you receive the whole block from the first miner, and he is then able to decide which transactions to include in his block. So essentially only when the miner finds a block in in this case 10 seconds does the network receive an empty block. In practically all cases that's not going to happen, and they'll get a full block anyway, and we won't have to worry so much about network throughput. The 10 seconds highlighted here is propagation time of a full block. This time can be influenced by many things. Bigger blocks can make it take longer. Network attacks make it essential to ask the original miner for some more details, which slows down the propagation time. And a very important one is something we see in the Great Firewall of China. Some countries just may not have such a great connection to the rest of the world. I don't think it's a good idea that a miner in Australia loses money just because he has a slower connection to the rest of the world. So the idea here is that optimistic mining means a miner is made immune to any propagation delays of the transaction in a block. And honestly, this can only mean good things to avoid centralization of mining power. In my designs, the teeny tiny part of the block a miner sends out as soon as he finds it will basically just be a block header, which is, what is it, 100 bytes? A node can validate this with a cheap check and then forward it. So this makes it really fast. Two details are important here. The data is forwarded by any node to its peers, and that's it. Just receive, check, forward. and there that means there is no more network traffic that a peer generates based on this. It's just a way to broadcast a new piece of data as fast as possible, as far as possible. Simple. I always like it. Keep it simple. As promised, these changes are mostly boring and really not Nobel Prize worthy. I still get excited from changes that have a substantial benefit though, so for me it's good. And yeah, I'm just that kind of geek. These changes do help a lot when you add them together with lots of other changes that we're working on, and we will end up with a massively better scaling system than what we have today. If we look at what it means to scale Bitcoin today, we look at all the obvious resources that any computer program needs. Most of them are really not an issue. For example, it would take 75 years to fill up a mainstream hard drive of 3 terabytes with today's block size. I'm pretty sure people will buy a new one before that time. People run a client on a Raspberry Pi, which really doesn't have that much processing power, and it copes just fine. So what we have realized, and there's universities publishing posts as well and saying the same thing, in Bitcoin the biggest scaling issue today is the inefficient use of bandwidth and a poor peer-to-peer network. This is demonstrated best by the usage of a centralized relay system, which operates outside of the Bitcoin network that miners use to send blocks to each other as fast as possible. As long as these centralized systems are needed, that means we will have a permissioned system where a new player needs permission to enter. New players that don't get permission to use the relay system that all the other miners are on will not be able to compete. We don't really want a system where the relay operator gets to decide what miners can and cannot do under threat of losing their access and subsequently their business. In Bitcoin we currently have what I label a first generation peer-to-peer network. Think about a system that students typically set up in class during computer science to play with. It's kind of making all the traditional mistakes. So further research I've been working on based on that is in Bitcoin, the network uses unlabeled binary blobs to send over the wire. This implies that developers can never really fix a message because old clients would not understand it and likely fail spectacularly. Tag formats, the most well known of that is JSON, solved this concept many years ago. What we need is like HTML, where old browsers can still read the newest format without giving errors. It just ignores the parts it doesn't know. So when I worked at a financial company sending out 500,000 stock price quotes every second, I learned a lot about how to do binary protocols properly. And I've done some extended testing yet based on that knowledge with a new on-the-wire protocol that looks like it's producing saving on bandwidth and speed quite substantially, but the real benefit is that it can be extended because fields are labeled much like JSON XML do. Its values are also strongly typed and extendable. What that means is that a protocol itself includes the information that says a value is an int, a bool, or a string. Making a change to switch to something like that is not a small one. It can be done perfectly backwards compatible, but it would be very beneficial to make the protocol more maintainable by allowing bug fixes to be made, which will be backwards compatible without any big changes in a clean manner. Another issue we have with a peer-to-peer system is based on how an individual node finds other nodes to connect to. We have some code that decides based on the IP address numbers whom to connect to. The logic seems to be that if you are are using a different group of addresses as known by IP address. That means you're on a different address, a different location. This is kind of overstating the correlation between addresses and distance, so honestly this is only slightly better than purely randomly choosing whom to connect to. So why is this important? Let's take an example of 2000 nodes, medium large network, right? All around the world you have those nodes, and the task is to get a message as fast as possible from one central node to everybody else, and central ionosphere is kind of everywhere, so it's not a centralized system. And my thinking is that if all the nodes measure the time it takes to travel between them, then you have a good map of what the distance is between every single node and its neighbors. And the thinking is, if you want to send a message from one side to the other side of the country or to the other side of the planet, you can send out a message to the next village, and that one gets it, reads it, and sends another message to the next village, and you'll eventually get to the other side of the world. But wouldn't it be much better if the first thing you do is send out 5 messages by plane to different sides of the world, and when they land they start sending messages to the local population, the next village? That would make the spreading happen much faster. So the idea is that a message would get to the other side of the globe in 5 jumps instead of 50. So to be fair, there's really not a lot of systems out there that create a peer-to-peer system of this scale, that have no central server and have to send messages through the entire system as fast as possible. But really, this lack of competition just means it's going to be a really nice challenge to find out what works and what doesn't. I can't be the only one that finds these kind of things fun. Some other details. We have some work done that fixes the problem that while downloading and validating a block, that node can't actually relay transactions, which is funny to know. That definitely can't be good for throughput. For a protocol to get a more professional level, we also really need message priorities. A simple concept. You basically get to push a node, push a message which is higher priority to the top of the queue instead of just appending it at the bottom. And we'd likely also want to support both TCP and UDP queues, where UDP, which is faster because it doesn't wait for a reply from the other side, is used for higher priority but smaller messages. This would be ideal for the optimistic mining teeny tiny block message we want to send around the world in near light speed. And last, we'd really need to set up a maximum size for a single message. The telecom operators switched to packet switching in the 1990s. We're kind of overdue. We now send a single message as 1 or many megabytes, which as a simple example is the block. That's 1 message. And experience shows that splitting that up into many small messages, maybe 50 kilobytes, and reassembling it on the other side will have a very positive effect on the throughput, because you can send bigger data to 2 peers at the same time using at the optimal solution only twice as long. But here's the thing. When you're sending a large block to a peer that is very slow in receiving it, this message chunking, splitting it up in smaller ones, will make the other peer that you're sending it to not slow down. I've implemented this on another system where the overhead per 50 kilobyte message ended up being about 14 bytes, so I really don't see any reason to not do this. These are lots of useful changes, what I'm hoping to see worked on, if not by me, then someone else. Other issues we will bump into as we get bigger blocks and higher throughput are going to be found. And I am sure we will fix them as we move forward. I have no doubt about that. This is the nature of the game. There is always some optimization that we haven't done yet. Beyond the network layer are a lot of other things that show up and being useful to work on in order to allow more data to go through Bitcoin cheaper and faster. It is still really young software, right? And I don't think it's been bothered too much with profilers and other speed measurements very often. There actually is a project that Gavin started, Benchmark Suite, in the Git repository. It unfortunately never saw any uptake by any of the other developers. Don't think they understand the concept. So please expect a huge amount of benefits to happen in the next years alone for throughput, as it's really easy picking for optimizations when it's not really been done before. I would say that within a year, the network will safely be able to handle between 20 and 50 megabyte blocks. And to step back from the technology side, creating a Bitcoin that on-chain can grow and support more users will be the thing that actually creates more value for the Bitcoin ecosystem. Imagine, more users. So while our opponents are discussing how to distribute the money of the rich differently until they inevitably run out of money, we are working to actually create new value to increase your wealth as well as ours. I think Bitcoin has a bright future. Thank you.
Hello. Thank you very much, Tom. If anybody has any questions, you can please type it into the Q&A box, and we will have Tom answer them.
Hello. So, can people hear me? Good. Let me see this Q&A part. I have one question here. You spoke on how a better peer-to-peer layout could help scaling. How can this be naturally occurring in a truly decentralized network? Yes, the idea essentially is that individual nodes know the distance to other nodes, and if you measure that using pings, for example, that's the distance on the internet, the amount of time it takes to go somewhere, you can essentially optimize at a very local level, saying I'm going to send data first to my further to nodes further away, and therefore have a better propagation time in total, because if you just send a message to somebody by plane first and then they start spreading it there, it's kind of like, you know, these nice graphics you see of things being forwarded over the whole world. I think it's really hard to explain this without graphics, but I don't know. The idea I have is a very simple one, and I'd like to see it actually be implemented. The problem currently is that the peer-to-peer system that we have in Bitcoin doesn't even know things like the distance between nodes. So I guess that's the first thing we have to work on. I'm going for the next question. Have you had a chance to look at the network rework stack, including UDP, that seems to be in progress by Core? I've had a very, very brief look at it, and my presentation tried to go over the whole system, the whole stack, and the various problems we have there. And I think a simple rework is probably a lot of work, and it's definitely something I want to talk with the guy that about what the intentions are, because there's so much stuff to be done that maybe you have to start from different positions, because it's not going to be backwards compatible unless you do it in one step anyway. So it's a little bit tricky there. I'm seeing another question: is work being done to split messages into smaller chunks? As far as I know, this project is not something that happens, and it really is not going to be easy or even possible to do that kind of work in the current stack. I have a strong suspicion it's also going to be very difficult in any project that is being done in core as well. When I did, I've done several peer-to-peer stacks in the past, and when I did a similar solution, it turned out to be a pretty major change in the way that stuff works. And when you start a new one, it's really easy, but it's really not that easy to do this if you end up having to fit it into something that has to continue working. So from that point of view, what Bitcoin now has are a sending of messages via a certain protocol, and I have the strong impression that the best way forward is to basically say, okay, that works, let's never touch it again, and then come up with a new stack that uses a different message format, uses a different port, and make that one be much better in features and in maturity. I have another question here saying, what's the minimum number of nodes that you feel is enough to be decentralized and secure? Oh, that's a very good question, because this is something that is really not easily to answer. This is really a question that is, it's both technical and political. And if you just look at a technical part of it, what it means to me is that, if you have miners sending stuff to each other, it has to go via a couple of nodes in order to be secure. If you have wallets that want to post new transactions to the network, it has to be done in a way that these transactions get properly checked for double spending. So initially there, I'd say maybe we need 200 nodes, and that'll be enough. At the other side, we have the political part. The political meaning, when you have a country saying, okay, now we don't like Bitcoin anymore, we're going to ban everybody, or we're going to even cut off the port for everybody, then you just might lose a substantial amount of nodes. So for decentralization, you would want more nodes. So maybe the 200 that I named is the minimum technically, but then you want maybe 5 times as many to actually have the overlap. And the 5 times as many, doesn't mean 4,000 of them should be in the US. You know what I mean? So it's a little bit of a trade-off in there. I do think that we're pretty generous on the amount of nodes we have currently. And there's another issue there in general. What we currently have in Bitcoin is we have 2 types of full nodes. One of them is essentially a full node that has all the blocks, and one of them that are nodes that basically only keep a minimum amount of blocks. They're called pruned nodes that basically cannot be asked for blocks in the past because they throw them away after a day or so. And this does mean that we need a higher number of nodes that have all the blocks in order to keep the network alive and keep people from being able to download stuff. I had an idea in the past that might be interesting there, is that we can take nodes that don't say, okay, we have to choose between 80 gigabytes or maybe 5 gigabytes of usage, which is a huge difference. Maybe we can say to a node, hey, it has 20 gigabytes, and then it takes the minimum it requires, which is essentially the same as a pruned node, and then the rest it stores a random set of nodes, a random set of blocks, I should say. And if you have enough people having a random set of blocks, then in the end, you will still have all of the blocks. And then you just need a new protocol message saying, give me that block, and the guy answering, oh, sorry, I don't actually have that block, ask somebody else. That might be a simple solution to making sure that you have all the history without having to have lots of full nodes with all of the blocks. Let me see, what other questions do we have? How did I first find out about Bitcoin, and what did you think of it? Oh yeah, this is actually funny, because the first time I heard of it, somebody was trying to explain to me, and I asked him, so what's the central server? And he said, there is none. Like, so how does that work? And obviously he couldn't answer me because he just heard the idea a couple of days before. And I didn't believe him. I just said, oh, okay, that can't work then. And I walked away until maybe a couple of weeks later, an article on the internet that explained it better. And I read up more on it, and I ended up saying, this is very interesting. And it wasn't very much later when this was around the time when the US busted the Silk Road for the first time, and the price went up quite dramatically afterwards, which is when I got really interested in the whole concept and started reading up like crazy. So that's, what is it, 2013, somewhere like that. Another question. The innovation is currently fragmented over several teams. Do you know of any progress towards an umbrella organization like the ETFs, RFCs that can serve the various dev groups? Do you think this is a priority right now at all? This is a very generic question. I think that's a very good question to ask, and I really don't have good answers to that. I do think that we are really not in a good place to do this currently. I've seen organizations reject changes like Exafin blocks because they are not defined in a BIP. The problem with the Bitcoin improvement process is that they are run by one group. So it's not really this concept. So we need something. I haven't seen any work towards it. I think it's really important to do that at one point. I probably am not the right person to do it, though. I'm more technical that way. Do you think it will always be possible to run a full node on extremely cheap hardware, like Raspberry Pi? A full node, if you define that as something that verifies all transactions, then I think yes. The amount of transactions I've calculated to go forward on how to make sure we keep on having a very rich set of features without having to give away distributed computing and all that stuff. I think that's going to be easy enough for that small amount of CPU. And you have to realize that a Raspberry Pi has, which is like $20, has the CPU power that not that long ago was really not possible for that price. So we are still seeing a lot of scaling in CPU power. And all Bitcoin has to do is use that to keep going forward. something I mentioned in my presentation, a full node essentially doesn't have to do anything other than being able to verify all the transactions and the block once every 10 minutes. The new block is being made. And currently, it managed to do that in maybe half a minute or various seconds, whereas a block only gets made every 10 minutes. So being able to keep up is perfectly fine as long as the CPU and the hard drive network manage to do it under the time consistently that the network makes blocks. So I don't really see any problems with that, even if we go to much bigger blocks. I don't have any other questions. Does somebody else want to ask a question? So the point of optimistic mining, which many people might know better as an old system called header first mining, is essentially to allow miners to continue working even while the network is still working on actually relaying the data. And there was one problem that people keep on repeating, is that what happens if a miner starts mining a ridiculously large block. And there actually is a very simple solution to that with this technology, with optimistic mining, is that if a miner sends a really big block out, it doesn't actually hurt any other miners, because they can just continue mining and just continue doing making money. And that basically is then a balance. If you have some miner mining a ridiculously large block, the only thing that will happen is that you get one or maybe two or three empty blocks after it, which settle out the average. And that way you basically get a much better average of the whole system. And this also answers some questions that people have been having about how do you specify how many blocks, how big blocks can be. So for example, if you have an algorithm that says, okay, we look at the last 1,000 blocks, they've been this full, then take that as the average size, then times 1.3, and that's then your new maximum block size. This also means that if you have a miner trying to manipulate the numbers, it won't actually happen, because the whole network as a community, the progress and the speed of relaying blocks ends up being a mask on how fast we can transfer these blocks. So smaller blocks are being sent out if a really big block is being sent first, pulling down the average and not ending up having any problems here. I see another question. What do I think of Bitcoin versus altcoins? Altcoins are, in my mind, and I guess I have to specify this, are basically coins that have a different genesis block, which means that, you know, Ethereum and Litecoin and all those things are there. I can look at it in two different ways. First of all, we have a altcoin that tries to just, you know, steal the ideas of Bitcoin and then make money on its own, or there is some more innovation going on. And most of the time that innovation on that much smaller space will definitely be useful. It's research essentially, and it will be definitely more useful to do that in a real economic setting than in a testnet. So on that note, I really like altcoins. I think it's a fantastic way of doing it, and I think there's a lot of ideas that can be done. On the other hand, something like Ethereum, it really is a competition in the way that we look at it. It's a competitor. They are taking the money that could also be in Bitcoin. They're taking the goodwill that could also be in Bitcoin. So it goes both ways. It's a balance. Yes.
I think there's we have about 10 minutes left until the next slot, but I think there's another great question that somebody, that Tom Slav said on the chat box, not the Q&A box. I don't know if you see it. It's about he's asking about the difference between compact blocks and extreme thin blocks, and whether or not that's something you want to comment on, or is that something maybe we should, or we can leave until that talk is made by the person speaking about that topic.
I have the impression that could definitely be better answered by Kronos. The speed, I think, is a very good question. What we currently have is one system, extremely thin blocks that have been published, that are in production, that on a private branch I have merged into the latest part of Bitcoin Classic that I'm still looking at. It's ready for merge, essentially. And then there's this other group coming in at a later time saying we're going to make our own. What I want to hear from them is how it's better, right? I want to see actual results from them. Why would I use their stuff? Because essentially, if somebody comes in and says, here's mine, then that's not really something I care about enough to actually do the speed optimization or the speed measurements myself. I think Core should publish something at minimum as useful as what has been published by the Bitcoin Unlimited guys, a fantastic series of actual numbers made accessible for everybody. And as long as that is not there, then it doesn't really seem like a very much of a competition to me.
Thank you very much, Tom. Thank you for your presentation, and thanks for everyone for questions.